All right, welcome back, and I really hope you are all okay after the cyclone. And so I didn't have internet connection for a while, didn't have electricity for a while, and so I mean many of us actually faced more complicated issues than this. But in any case, I think most of us are fine now, and so I think I thought we could start. And again, please let me know if the audio quality is fine with this. So after today's class, we shall have one more class on this, and that will be the end of this subject for this semester. So, I mean, yeah, we shall talk about the midterm examination separately, okay? And very soon, don't worry. And the topics we are going to discuss today in this particular class are basically how we analyze frequency responses using a certain standard. Okay, so we shall start. And we shall discuss. So these are the things we are going to discuss in today's class. All right. So we are going to discuss something called logarithmic scale and something called decibel scale. You might have heard the word decibels. Okay. And we are going to discuss that in proper details today. Something is going wrong with the live stream. Let me just refresh that. All right. Something was actually wrong with the live stream. Anyway, sorry. All right. So we're going to discuss these, but kind of as usual, we are going to start with a certain philosophy so that actually we can have a certain idea before we can actually jump into the mathematics of this subject. All right. So since I mean many of you are already here, let's start our discussion today. All right. But I shall give you a certain, what should I say, certain real life perspective on the topic, and then we shall try to move on to frequency response analysis and how we can apply our real life ideas or rather real life feelings into our subject. We shall have that discussion. So let me ask you this. For example, maybe you are in a room, for example. Okay, just to give you an idea how we perceive things. Let me give you an idea on how we perceive things, how our sensors, like our eyes, okay, our ears, these sensors perceive things. For example, okay, we have a light sensor, right? We have light sensors. These are our eyes. Our eyes are light sensors. We have pressure sensors. For example, our ears are pressure sensors. So we have these sensors built in within us, right? For example, and with that said, let me give you a very simple example to demonstrate what I mean here, or what I am going to teach you here. Okay. All right. Say, imagine you are in a room, right? And a completely dark room. Right? You are sitting in a completely dark room. There is absolutely no light whatsoever, right? Okay. Try imagining something like that. Okay. And say there is a single light. Okay. Maybe a bulb or something. Okay. Now it's glowing, for example, right? Of course, you would now be able to see the light, right? Everything will brighten up automatically, right? Nothing will be not everything won't be complete. You won't be completely in a dark room, right, anymore, because you have a light, right, in that room. This is understandable, not a very difficult thing, right? You have one light glowing, for example. and you can feel the light automatically because of your light sensors, because of your eyes. Okay, got it, right? Very good. Now imagine right next to the light that is glowing currently in a completely dark room, I have put another one. Okay, identical in nature, identical in wattage and everything. Okay, and I put that in the same room right next to the light, right? And both of them are glowing now. So would you feel the difference? Question is, would you feel the difference? Actually, yes, you shall feel the difference, and it will feel that the amount of light has doubled, right? It will feel that the amount of light has doubled, right? You felt that, and you would actually feel that quite well. Okay, if you have just a single light in a room, and if you put another one, you would automatically feel that the light amount of light has actually doubled. All right, very clear idea, right? Very simple idea. Now imagine you are in a stadium. Now imagine this: you are in a stadium, okay, and stadiums are lit through floodlighting, right? Imagine like that. So maybe in the set of floodlights, you already have, say for example, 100 floodlights that are working, right? Imagine you are in a stadium which is being lit through floodlighting, and say for example, 100 of them are lit properly. Okay, right? You will have a automatic feeling of the amount of light that is there. Okay, right in the stadium. Okay, no issues with that. Now if I connect one more light, if I add one more, okay, now that I have 101 lights, okay, identical in nature, all the lights are identical in nature, right? So previously the situation was the amount of lights was 1, and then I added one more, so right, but you would feel this change, that there was an increase of the amount of light by 1 unit here. You would feel the change, right? But what about this one? Say 100 identical lights are glowing, okay, in a floodlighting situation, maybe, okay, maybe in a stadium. Now if I connect one more, question is, will this change be visible to you? Question is, will this change be visible to you? Right? So I think you know the answer, right? If in a floodlighting situation you have 100 lights working, right? I put another one, identical in nature. But would that change? Yeah, this plus one won't be kind of visible to you, right? That change will be negligible for you, right? Even though the amount of light that is increasing here in both the places, so the amount of light is increasing by 1 here, and it is also increasing by 1 here, right? So as far as the mathematics goes, the increment is identical in both places, right? But you won't have any what should I say, any significant feeling about the change, right? As a human being, we won't have any significant feeling about the change. Is that understood? Yeah? This is true, right? All right. Now consider one more situation. Okay, so imagine you are going to a shop. Okay, imagine you are going to a shop and you want to buy two things, and those two are essential commodities. You have to buy both of them. Okay, and there is one item here which usually costs 100 rupees, say. Okay, which usually costs 100 rupees, and there is some other item that actually costs 10 rupees. All right, all right, got it, right? Fine. So this item has a marked price of 100 rupees and this item has a marked price of 10 rupees. Got it? Got it. Now you want to buy both of these, right? So you have exactly 110 rupees with you, and you want to buy these two equipments, these two things from the market, right? Now imagine that there are two shops. For example, there is one shop here, rather one shop here and one shop here. And imagine there are two shops here, and imagine they're giving you discounts. They're giving you discounts, right? And how do people write discounts? And this is how they write discounts, right? They would cut the original price and they say, okay, I'm giving you this for 95 rupees instead. But this is exactly, you have to pay 10 rupees for this, right? Got it? So in total, so you got a 5 rupees discount on this, right? And there is no discount on this. And in total, you are going to pay 105 rupees for the total thing, right? Got it? So you went to a shop. So there are two shops from which you can buy both the items that you want to buy, right? Now one of them is giving you a discount of 5 rupees on the 100 rupees item, so that you are going to get that for 95, and the other one will be 10 as usual, and the total will be 105. Now imagine you are actually in this situation, and there is another shop which is not giving any discount on this. The item that costs 100 rupees, no discount is being given on that. And the item that is sold for 10 rupees, this particular shop is giving you a discount of 5 rupees on that particular item, right? So instead of selling it for 10 rupees, they are now selling it for 5 rupees. So that once again, you have to pay a total of 105 instead of 110. So here in this shop, you got a total discount of 5 rupees. In this shop also, you get a total discount of 5 rupees, right? But in a slightly different way, so that the total amount you are actually paying, okay, by going into either of the shops will be identical. You are going to pay 105 rupees no matter what. But the discount that is given by the first shop is on the first product, where it actually costs 100 rupees and you are getting a 5 rupees discount. So you are getting a discount of 5 rupees on a 100 rupees item. And here in this shop, you are getting a 5 rupees discount on an item that costs 10 rupees. Overall, you got the same discount. Now think humanly and tell me, would there be any difference in your feeling about the discount that you got? My question is this: would these discounts that you actually got or that you actually get from these two shops feel identical to you, or would there be any difference in the feeling about the amount of discount you received? So you tell me that. I won't tell you, but you tell me, under this situation, would the discounts feel identical, feel the same, or would somehow one of the shops would feel or would it feel like the one of the shop is actually giving you a better discount? So one of the shops is giving you a 5 rupees discount on an item that costs 100 rupees, and one of the shop is giving you a 5 rupees discount on an item that costs 10 rupees, right? What do you think we would feel like? Just imagine going to a shop, right? And you trying to buy something that usually costs 100 rupees, and someone is giving you that for 95 rupees. Of course, you got a discount, right? And imagine you are again going to another shop and you are trying to buy something that usually costs 10 rupees, and the shopkeeper is giving you that for 5 rupees. Which one of these discounts would feel feel like a better discount? I think you get my question, right? Which one of these would feel like a better discount? Yeah, one of you actually calculated the percentage of discount, right? Okay, none of the jokes apart, none of the products are defective, identical products. Okay, No issues with. I mean, I'm saying which one of these discounts would feel like a bigger discount to you? Would the two discounts feel like identical discounts to you, or would there be any difference in your feeling? Right? So in general, what happens is that if you get a 5 rupees discount on something that actually costs 10 rupees, this discount would feel bigger, right? Right? Because in your mind, you would feel that you got only a 5% discount on this. In your mind, you would feel like you got a 5% discount on this. And in your mind, you would have a feeling that you got a 50% discount on this, right? Right? That's understood. So there is, I mean, you are getting the same amount of money off, right? So some of you are saying that you would like this discount better. I mean, no, not really. Do you think this would feel lucrative to you, or rather a bigger discount to you? Actually, at the end of the day, you are paying the same amount of money in total. At the end of the day, you are paying the same amount of money. Okay. At the end of the day, you are paying the same amount of money, right? Yeah. So the point is, this is being sold for 95 rupees and this is being sold for 5 rupees. Okay. So in total, you are going to pay 105 rupees no matter what. Yeah. But even though you would be paying the equal amount of money in both of the shops, because these two are both of them are identical essential equipments. You have to essential commodities. You have to buy both of them. Yeah, the total amount of money you will be paying would be identical, same, right? If you go to this shop, you will be paying 105, and if you go to this shop, you shall again be paying 105 rupees. But the discount happened in a different way, right? And you would automatically have a feeling that this discount is smaller than this discount, even though the amount of money you actually saved was identical, right? The amount of money that you actually saved was identical, right? Got it? I think we human beings, usual human beings, have a feeling like that, right? Okay. Let me give you another example. Okay. Maybe when you go to an online store or something, okay, what do you see? Maybe you are going to buy a mobile phone or something. You see that the mobile phone you are trying to buy actually costs 9,999 rupees. All right. So maybe you are going to buy something that costs exactly 9,999 rupees. I mean, have you ever put a thought to this? And why exactly is this? Why can't they write 10,000 rupees? Why can't they write 10,000 rupees? Why would they write 9,999 rupees? Yes, about this, we always think about in terms of ratios, right? Here, and I will tell you the underlying philosophy here, but tell me, why do you always see that things are priced like that? 9,999. Why like that? Okay, you wanted to buy something maybe yesterday and you saw that the price of the product was 9,999 rupees. Is it for saving tax? No. In India, tax is calculated in a proportional rate. Okay. Electronic equipment, probably you're going to pay 18% tax, no matter what. Okay. It's just exactly 18%. No one is saving anything from here. Yeah, the problem is in the number of digits. That's absolutely right. So if I tell you the product costs 9,999 rupees, in your mind, you first see the number of digits, how big the number is. Now, instead of saying this, if I tell you it actually costs this, you immediately see more number of digits. You immediately see more number of digits, right? This number has 4 digits and this number has 5 digits. Even though there is just a difference of 1 rupees between these two, this number would feel bigger, significantly bigger in our mind. Psychologically, this number would significantly feel bigger than this one. Yeah, they won't give you 1 rupees back, but the thing is, this number actually feels much bigger, much bigger. And that's also true for other digits, where the digits other numbers where the digits don't change. Maybe you are buying something and that costs 17,999. Same idea here. Instead of saying 17,999, if I say 18,999, now the philosophy instead of, if I say it's exactly 18,000, now the philosophy is somewhere else. The philosophy is in the larger digits. The idea is that, again, as usual, we start reading from the left, and from the left here we see a 17. In our mind it acts like a 17, and here in our mind this acts like an 18, right? So this automatically feels much larger, or rather bigger, than this. No. That might be a conspiracy theory. Okay, that 1 rupee is not kept as a count or anything. Okay, we have much better ways to keep count of things, so don't worry about that. Okay, the idea here is that this number would feel smaller than this number. Okay, because first we look at the more significant digits, right? And then we go for the lower significant digits. I mean digits that are less significant, right? So with that said, this number would automatically feel bigger, right? Someone say, yeah, 18,000, right? Something like that. And instead of saying that 17,000 something, right? This immediately goes to that something category. You know. So here there is an increment in number of digits. This would immediately feel significantly bigger, and this would again feel bigger because there is a change in number in the significant figures or significant digits. Yeah. So is that understood? Is that philosophy understood? Right. So I think this usually happens. I mean, this automatically happens in all of us, because after all, we are all human beings, right? Right. Again, this is the entire philosophy behind pricing pricing things like this. Why would they price things like this? Okay, simply because to keep the more significant digits smaller. That's the idea. There is no other philosophy on that. Because as human beings, we look at these numbers and automatically we have a philosophical, psychological understanding inside our head. Okay. All right. So with that said, now let me give you another example. Okay, let me give you another example. Okay, let's say about human age. Right? What happens is when you were when you were children, of course, all of us were used to be a child once upon a time, right? When you were children, it might have felt, or you probably you remember that in your childhood days, I mean, time did not really pass, right? Okay, days felt quite long, for example. But as you grow up, what happens? As you grow up, or of course, you people are in your 20s, and as you will move on to being in your 30s and 40s, you'd probably remember what I'm saying today is that time would automatically feel like time is flying, right? It would feel that time is flying. It would feel like the days are becoming shorter. And it would feel that you would have less and less amount of time in each day, right? When you were children, it felt like days were pretty long, time does not really want to pass and something like that. But as you grow up, as we human beings grow up, okay, and as we get more and more responsibilities in our life, what happens? The exact same amount of day, exact 24 hours feels shorter. Automatically these days and this time would start feeling like they're pretty short. As the saying goes, time flies, and time starts flying when we keep growing older. As we grow older, time keeps flying at a faster and faster rate. That is exactly what happens, and this is kind of a feeling that you need to have in order to understand this, right? And hopefully you will understand maybe in the next 10 years and 20 years. All right. So remember, you people are in your 20s now. Yeah, and now probably you don't have any responsibility or anything, for example. Okay, you're just you are a student and so and all. And the thing is, this is not just about responsibility, right? And ask your parents, and if you're fortunate enough to have your grandparents, ask them, and they will tell you that they have fond memories of their for example, say if your maybe your grandpa or grandma, maybe he or she is like 80 years old, maybe. Just let me give you an example. And if you ask him or her that the grandpa, what do you remember from your childhood or maybe from your young age? Maybe your grandpa would tell you many lively stories from his rather childhood, I would say. Okay, maybe he would tell you stories from when he was less than 30 years old, maybe less than 25 years old. Okay, something like that. So he will probably tell you stories, many fond stories when he was younger than 25 years, for example, right? And then you would hear many stories when he was kind of older, right? And this is what exactly happens. As you grow old, you automatically get less and less memory or less and less amount of things to remember automatically. Okay, this is the idea. Okay, if I ask you, at what age would you graduate? At what age would you graduate? The answer would be, of course, yeah, 21, maybe 22, right? At what age would you get a job? Maybe 21 and 22. At what age would you marry? Maybe before 30, and so on, right? So most of the important events in our life take place before we are even 30, right? Most of the important events in our life. Okay. So if I ask you this, so for example, when you grow 80 years old, and if somebody asks you what are the most important events that happened in your life, most of them would have happened to you before you are 30, right? So we keep a fond memory of things that happened to us before we were 30, maybe before we were 25 and so on, right? But as we grow old, we get to have less and less amount of significant events that happen in our life, right? Maybe ask your grandparents, maybe ask your parents, what significant thing happened to you when you were like between 40 and 50? Probably they won't say nothing really. Okay, something like that. Maybe some significant thing, right? Something like that. So as human beings, that is how we perceive time. The perception of time, this is how we perceive time. For example, someone who is 5 years old, say someone who is 5 years old, okay, maybe a child who is 5 years old. For that child, 1 year is a very long amount of time, because for a 5-year-old kid, 1 year is 20% of his or her entire life, right? So for a 5-year-old child, 1 year is a very long time, because 1 year is 20% of his or her entire life, right? So someone who has lived for 5 years, for that person, 1 year is a very, very long time, right? Similarly, someone who is a 10-year-old person, okay, a 10-year-old kid, 1 year is still a very long time, because this is 10% of his or her entire life. Get the point, right? But someone who is 50 years old, like me, someone who is 50 years old, okay, what about 1 year? Someone who is 50 years old, for that person, 1 year feels like 2% of their lifespan. Try to get the feeling. Okay, I have lived for 50 years. For me, 1 year, how much 1 year feels like? 1 year feels like just 2% of my life, right? I have spent 50 years of life. How much would 1 year feel like? 1 year would feel like 2% of my life, right? This is just like the discount, right? Even though the time span is exactly the same. Okay, 1 year is exactly the same for a 5-year child, 5-year-old child, 10-year-old kid, and a 50-year-old man, right? But exact the amount of time it would feel like would be very different, right? And that's a joke there, right? The idea is that if you want to lie about your age, always lie up, right? And so people would say, okay, you look pretty young for a 50-year-old man. Yes, I look pretty young for a 50 years old man, right? Anyway, so the idea is that for a 50-year-old man, the 1 year would feel like just 2% of his life, right? So that is how time really flies. Okay, when your parents or grandparents say time flies, that is how time flies, because our perception of time automatically gets reduced as we grow older, right? So in all of these examples, all of these real life philosophical and practical examples, okay, on all of these real life and practical examples, what you have seen is that in our mind, things do not add up, but things do multiply. Again, let me just rephrase my statement here. Okay, we always have a multiplicative understanding of things. Okay, we do not really have an additive understanding of things. Our brains do not work linearly. Just to give you an example, just to explain everything here, when I had one light in our room and then I added one, this change from one light to two lights, that change did affect your brain, and that automatically did affect your brain, and that automatically felt like a significant change, because our brain automatically calculated the change in terms of a ratio, not in terms of how much was added, right? Only one light was added, but our brain did not calculate the change in terms of how much was added, but how much was added in terms of the addition, but in terms of the ratio. Our brain automatically calculates the ratio of changes, right? So here, how much was changed? 100% was changed. There was a 100% increment, right? So from one light you went to two lights, so you had a 100% change. But our brain did not perceive the amount of change as an addition, how much increased, not in terms of an addition, but in terms of a ratio. How much did change? 100% increased, right? But in here, our brain again did not calculate the change as an addition, right? It did not see that one light was increased. It only saw that 1% of the light was increased. From there were 100 lights, and now we have got 101 lights. So only 1% of that was increased. That is simply because this was 1% in our brain. Our brain did not perceive anything. And what is a percent? Percent is basically a ratio, right? Right? So this is the multiplicative understanding of things. This is how our brain understands things multiplicatively, right? And here you are pretty quick to understand that this discount would feel like a smaller discount simply because this was a 5% discount, and this discount would feel like a bigger discount simply because this was a 50% discount, even though the amount of money you actually saved was identical, right? Here you saved 5 rupees, here you saved 5 rupees, but this amount would actually feel like a bigger amount because your brain automatically calculated things in terms of the ratios. And here also, in number of digits, and like that, we automatically calculate things in terms of ratios. And again, this is the easiest example to understand. As we grow older, the same amount of time feels like significantly smaller to us, simply because we automatically the perception of time in our mind is based on how old we are. Okay, the perception of time in our mind is entirely based on how old we are, right? Got it? So for a 5-year-old person, 1 year is like a 20% of his entire life. So this is pretty big. Okay, and for a 50 years old person, 1 year is like 2% of his entire lifespan. Okay, so compared to a 50-year-old person, for a 5-year-old child, 1 year would feel 10 times as much or 10 times as long here. Okay, so again, our perception of time as human beings, this is entirely based on our present age. Okay, how long a day would feel or how long our years feel, that entirely is based on how old we currently are. So that's again the same feeling, right? So we have been talking about so many things, and this is to give you the idea that everything is kind of multiplicative in nature. We understand things in terms of ratios, right? All right, and why again and again, just to tell you very quickly, same thing happens for our ears. For example, okay, maybe a sound box is playing, and if I double up the audio, you will automatically hear that sound doubled up. Okay, and same thing if 100 sound boxes are playing, for example, if I add another one, that change won't be felt by your ears. So previously you saw our eyes are sensors, like eyes do calculate things in terms of ratios, our ears do calculate things in terms of ratios, and everything, all of our sensors do calculate everything in terms of ratios. So we feel changes in terms of ratios, not in terms of how much was added or how much was decreased. Okay, not in terms of an addition, but in terms of a multiplication. Okay, that is how our brains do perceive things. And what is happening today is the YouTube streaming client here is actually hanging, unfortunately. I'm not sure why it's happening. I'm getting to refresh this again and again. All right, so with that said, maybe I don't understand, maybe the current value of the thing that we are trying to have a perception on is A, and the value actually changes to B, maybe increases to B. Okay, we had a value of current value of something that was A, and maybe that changed or increased to a value B. And again, as far as our human perception goes, we won't feel the change. So this is how the change we feel. So we do not feel the change to be like this. We do not feel that there was a change like B minus A. This is not what we feel, but this is what we feel. We always feel changes in terms of ratios. This is what we actually feel, right? We feel the ratio of the change. Okay, we don't feel the difference of the change. Don't really feel that. We feel the ratio of the change, and that's true everywhere, right? Now tell me, what is that mathematical operation that when applied on a ratio actually gives you a subtraction, for example? So now try to understand that as human beings, we always see ratios. When we always see changes in terms of ratios, not in terms of how much we want to add or subtract or something like that. Now try to understand, if I apply log on this, now logarithm has a very wonderful property that this happens. This is log B minus log A, right? Now we do not really feel the difference in absolute difference, right? This is called an absolute difference. Okay, take this value, subtract. This is called an absolute difference. We do not feel the change as absolute differences, but we do feel the change as ratios. And if I take a logarithm on ratio on a division like that, okay, that automatically changes into a subtraction here, right? So again, just to tell you, we do not feel like a change that happened in absolute values like that, but we do feel like a change that happened in this way, right? Try to understand. Did you understand the term? Okay, so we do see the difference. So this is the difference and this is the ratio. We call this the difference. This is the ratio. So we see this, we don't see this. So in absolute value, we don't see the difference, right? Got it? In absolute value, we see the ratio. But if I take the logarithm, then what do I see? We see the difference. So we perceive the difference, of course, how much increased or how much added, how much got added, how much got subtracted. We see that in terms of difference, but not in absolute scale, but in logarithmic scale. So in other words, our brain, okay, our mind, our eyes, our ears, all of our sensors do perceive things in ratios, or in other terms, they perceive things in logarithmic scale. they perceive things in logarithmic scale. So we perceive things logarithmically. So which means that if there is a change in multiplicative order, we see that, we feel that, because that results into a subtraction or an addition here. Okay, you get the point, right? So that is how all of our sensors and even our mind are logarithmic in nature. We measure everything in terms of ratios. We feel everything in terms of ratios. And that is why all of our sensors are logarithmic in nature. And things would have been really bad if this wasn't the case, right? Is that understood? Feel free to ask any question that you might have. And in practice, we have plenty of logarithmic scales to explain many things, right? You have heard the term decibels, right? Right? You have heard the term decibels, right? In short, we write dB, and we're going to discuss that today. Okay, so that's again something like a logarithmic scale. We shall discuss all of these today. So I hope this philosophical background is clear to you, that as human beings we perceive things multiplicatively, and multiplication automatically results into an addition or subtraction in logarithmic scale. So if I have to think about differences, yes, we think about differences, but in the logarithmic scale. We don't think about differences in absolute scale. Okay, that is how the changes we feel, right? You get the idea? Okay, all right. So with that said, let me jump to the understanding here, and let me give you something that you need to rather understand properly, right? Now let's go back to this, our ears, right? Maybe when you were children, you learned that our ears have a effective frequency range that we can hear from 20 hertz to 20 kilohertz, right? You probably heard that, right? So we said probably you heard that we can hear effectively from 20 hertz up to 20 kilohertz, right? We probably heard that, right? All right. All right. Nice. Now my problem here is that if I give you rather an audio device, for example, an audio device, something like a speaker or something, okay, that is producing audio so that you can actually hear it through your ears. Okay. Now, of course, those who listen to music, we have certain words, right? We say bass, and we say mid-range sound, and then we say treble, right? Right? We have bass, so something like this. We have bass, then we have mids, and then we have treble, right? So we have bass, we have mid-range sound, we have trebles. So trebles are high frequency sounds. Then we have mid-range sounds where the human voice and or this kind of vocals lie, and right, and then we have bass, right? We have that, right? Bass are all those heavy sounds, right? So can you tell me the frequency range? So can you tell me the frequency up to which we consider that to be a bass or a heavy sound? Can you tell me the frequency up to which you consider that to be a heavy sound? Let me open up something. Let me do that for you. So you probably have heard about this, right? Let me just set something up. All right, let me jump to this. All right. All right, right. So let me make sure that this actually works first. I'm not sure if this is going to work. Thanks to the beauty of OBS, if you have a earphone or a headphone right now with you, okay, you're listening to this through using a headphone or an earphone, you probably heard a very low frequency sound, right? I just generated a sine wave that works at 200 hertz, right? So this is a 200 hertz sine wave. Just hold on, YouTube is giving me too many errors. Just hold on for a while. YouTube is giving me too many errors. It is saying that some error has occurred, but from my point of view, nothing happened. You are getting the stream right, right? I hope you are getting the stream right. Okay. So I will lower the volume for the next few things. Okay. For example, let me increase the frequency to a 300 hertz. So this is now going to be a 300 hertz sinusoid. YouTube is giving me too many errors. What is happening? Today my network is fine, but YouTube is giving me trouble. Something is wrong. I hope I'm live. All right. All right. So now I have generated a 300 hertz sinusoid. So this is now a 300 hertz sinusoid. Let me play that. I have decreased the volume so that your ears do not burst automatically. So let me mute myself. That was 300 hertz sinusoid, right? So you can feel the difference between a 200 hertz sinusoid and 300 hertz sinusoid, right? You can feel the difference, right? Because the frequency increased as a ratio, right? Automatically. You got the point, right? Now, so of course, what was the ratio here? So the frequency increased by a ratio of 50%, right? So the frequency increased by 50%. So let me go back. So this is again, this is for those people who are using some kind of a headphone. Otherwise, you would be hard pressed to listen to this. Yeah, then YouTube's compression is there. My point is, right? You can hear this sound, right? So this is 200 hertz. And if I double the frequency, right? If I double the frequency, so for example, or rather if I increase the frequency by 200, right? So I now have 400 hertz. 400 hertz. Can you feel the difference between 200 hertz and 400 hertz? This is 400 hertz. All right. This is 400 hertz, and previously we had 200 hertz. So could you feel the difference that the frequency actually changed? yes, you could feel the difference, that frequency actually changed, right? So how much was the change in frequency in terms of absolute value? The frequency change in terms of absolute value by a 200 hertz, right? The frequency increased by 200 hertz, right? All right. Now look at this. This is a 1000 hertz sinusoid. All right. Pretty weird, right? 1000 hertz sinusoid, right? Now if I increase the frequency by 200 here, if I increase the frequency by 200 here, the point is there was a change, but the change wasn't that significant, right? Now I would reduce the volume even further so that, I mean, you don't get a brain damage from this, and I would make the sound shorter. So this is going to be a 5000 hertz sinusoid. Okay, 5000 hertz sinusoid, so 5 kilohertz sinusoid. I'm not sure how much you will be able to hear, again thanks to YouTube's compression, but let me try. Right? So this is 5000 hertz sinusoid, right? I'm reducing the volume once more. Hold on. That was a 5000 hertz sinusoid. Good. So now if I increase it by 200 hertz, it hardly feels any different, right? You won't be able to figure out the difference between these two frequencies, right? The change in frequency would not be significant. You won't have a significant feeling about the change in frequency, right? Is that understood? I think it's understood, right? You get the feeling. So my point, what I was talking about earlier, is that for the low frequencies that we call the bass, we have a frequency range of around 20 hertz, which not really any headphone can produce. Okay. Yeah, you only hear a little difference. The bass is from really 20 hertz to about 150 hertz. And again, these are just rough estimates. Okay. So anything that happens between 20 hertz and all the sounds that happen between 20 hertz and 150 hertz is considered to be a bass, right? Yes, of course you felt a little difference, okay, but that was a little difference compared to a change that happened from 20 to 200 to 400, right? So if I increase the frequency from 200 hertz to 400 hertz, that change was way more significant, right? Because that was a 100% change, really, right? That frequency change was way more significant than this change, right? So now mid-range frequencies that we have, that we say we have, the mid-range frequencies are from 150 hertz to about 1.5 kilohertz. So rather from 150 hertz to, so this is again just some rough values, okay. And the treble frequencies are from 1.5 kilohertz to 15 kilohertz and more, for example. I'm saying 15 kilohertz because our human ears cannot really hear higher frequencies. Right? If I make you hear from like higher frequencies above 15 kilohertz, it would be hard place to hear. And again, this 20 kilohertz into 20 hertz is again absurd, pretty absurd. This could be 35 hertz and so on, right? Because not even very good quality headphones that cost thousands of rupees, maybe 1 lakh or 2 lakh, something like that. Those kind of headphones can't even produce these low sounds, right? Unfortunately. Again, even if the headphones produce that amount of sound, our ears won't be able to hear. So yeah, really this frequency range is from about 35 in practically this is actually the frequency range we can actually hear. This is the practical limit, and this is kind of the theoretical value, the frequency that we can hear. Now you can understand that changes that happen in that small frequency range is significant to us, right? This is these frequencies would feel like very heavy bass, and these frequencies would feel like light bass, right? For example, okay, these frequencies, very low frequencies, this would feel like a bumpy heavy bass, for example, okay, and these frequencies won't feel like that, but this will still count as bass. Now the frequency I'm talking. Okay, and that is the thing. Someone is saying, does age make difference in hearing sounds? Absolutely it does. Okay, as you grow older, as you, for example, when we were, for example, when we were children, okay, our voice used to be like a little sharper, right? Of course, right? Little sharper. But as we grow old, our voice become deeper, right? Why does that happen? Simply because everything in our throat automatically becomes thicker and heavier. So the frequency at which they can vibrate automatically decreases. Okay, when we were children, the things that make noise or make sound inside our throat, okay, those were thinner. Okay, everything could vibrate at a higher frequency because they were thinner. And as we grow old, this our entire vocal cord and everything, they become thicker, and accordingly our voice becomes deeper, right? Is it understood? So deeper voice means we have a lower frequency components, more lower frequency components, more heavier components, for example. Same thing happens to our ears. As we grow old, our eardrums, everything, they become thicker and more stiff, right? So they only vibrate at lower frequencies. Okay, higher frequency sounds are kind of ignored, for example. Understandably, right? So what happens is, as we grow old, the frequency response of our ears, the frequency response of our eardrums, of our vocal cord and everything, those change. Okay, the frequency response of everything, all those things change. And maybe your grandparent, if you have a grandparent, probably they have a hearing aid, and if they have a hearing aid, they probably went through certain experiments, okay, on their ear, right? Right? And they probably, the ENT doctor probably did measure how well the ear responds to different frequencies, right? They did make a frequency response chart, and from that they tuned the hearing aid for that particular person. So all the hearing aids our grandparents actually use, okay, those are tuned to specific persons based on how their ears respond to different frequencies. Okay, so our frequency response of our ears, our throats, everything, those change. Okay, and not just ears and throat, our eyes, everything, all the frequency response of every sensors in our body, they do change. Okay, so that does happen. Okay, so all these things we are actually studying, these are abstract ideas, but they do directly apply in real life situations. Right? So this is how the frequencies take the sound we produce change, right? And again, as human, say for example, I'm speaking here, and the frequency range that I have, for me particularly, is from 350 hertz to about 3.1 kilohertz. So this is my frequency range. And how do I know that? Of course, I can record myself, and I can do a Fourier transform on that, right? I can record myself and I can do a Fourier transform on that. And when I apply the Fourier transform on my voice and plot that, of course I would get to see the Fourier transform plot, okay, the frequency response. Okay, so for example, so if this is f is in hertz, okay, this is basically omega by 2 pi, right? And this is the amplitude response of my voice. So then if I did that, and then if I plotted the frequency response, of course this is some arbitrary plot, but the plot kind of looked like this, and this range was 350 hertz, and this is like 3.1 kilohertz. So all the frequency components, or the most of the frequency components in my voice, lie between these two frequency ranges, right? Okay, you get the idea. Okay, if I had a deeper voice, probably this lower frequency range would be even smaller. Okay, if I had a more sharper voice, of course this would have been probably higher, something like that. So we have frequency ranges like that. Those who sing songs, they probably have a better, higher frequency range, wider frequency range in their voice, okay, and such. So this is usually the general frequency range of human voice, for example. Okay. Now, why am I telling you all these things? Because that is exactly how we figure out frequencies, or how we figure out frequency responses for practical systems. Right? So what happens is we feel changes, or rather we feel small changes in lower frequencies, and we only feel large changes in higher frequencies, because we only feel changes in terms of ratios, right? We feel small changes in lower frequencies and large changes in higher frequencies. Just take the previous example. Yes, someone is saying people working in opera. Yes, actually, right. So if you're in opera, you are training your voice, right? Those who sing, they train their voice. Okay. Of course, if you train your voice, of course, you would have a different frequency response than others, understandably. Take this example, previous one. There was a 100% change here. If there was a 100% change here, and that change was felt by us. Now, if there are 100 lights in the floodlight, and if I add 100 more, instead of adding one more, if I add 100 more, in that case, that change will be again felt, because that was again a 100% change. You get the point? So if we already have a higher amount of things, then if the change is high enough, okay, then we can feel that. Similarly, if the things we have is small already, then small changes are felt, right? So if we are already standing at smaller frequencies and there are smaller changes there, we would feel that. Similarly, when we are standing in higher frequencies, then if there are higher changes, larger changes, we would feel that automatically, right? So that is what happens, really, understandably, right? So now let's jump into the mathematics and how we figure things out. Let me pull a plot here. Let me try doing that. Hold on. All right. My question to you now is that, have you ever seen a graph paper like this? Have you ever seen a graph paper like this anywhere in your life? Unfortunately, unfortunately for us, usually what happens is I buy these graph papers in bulk, and in the class I distribute these graph papers to the students so that they can have a hands-on experience with this. Unfortunately, we cannot do that right now. Okay, and these graph papers aren't sold everywhere, really. Okay, and have you seen a graph paper like this? Probably not, right? You haven't probably seen a graph paper like this. But the point is, these graph papers are quite rather usual ones while discussing frequency response. Yes, someone says that it is used to measure sound. Not really sound, but if you are buying a high-end audio equipment, this is used to measure the frequency response of that high-end audio equipment. So if you buy some high-end audio equipment, maybe high-end headphones, or maybe high-end some audio equipments, high-end microphones, they would probably give you something called the frequency response chart of that audio equipment. Okay, maybe in the box, maybe inside the box as a pamphlet or something, they will show you the frequency response chart from of that particular item. And for that, they use this kind of a graph paper. Okay, and I'm going to tell you how this kind of graph papers are read. Okay, how you read this kind of graph papers. Okay, but the idea is, yeah, some of you probably have seen this kind of a graph paper, and some of you probably haven't seen this kind of a graph paper. But let me tell you how this kind of graph papers really work. But before I tell you, let me just mark this graph paper, because try to understand this vertical axis is not a very difficult thing to understand. This vertical axis is just like any other graph paper, right? This vertical axis is 1 centimeter apart. So this vertical axis is just like a simple regular graph paper, right? But this horizontal axis is not. So let me describe the horizontal axis. So there won't be any issue with the vertical axis because that's identical to all other graph papers. Let me tell you about the horizontal axis, how the horizontal axis is actually read, right? Yes, in many places this kind of graph papers are used, not just in our frequency response studies, in many cases, and you will soon see why, right? All right. So let's start very simply. Say again, pay very close attention here, and anytime if you feel that you don't understand something, that feel free to ask. Okay, say this is 0. Of course this is 0, this axis is 0. Let me write it here. Say this is 0. Okay, and this is 1. We are considering this entire thing to be from 0 to 1. Got it? So this would be 2, this would be 3. Is there any issue with that? I think not. There shouldn't be any issue with this, right? All right. So we are starting from 0. We have 1, we have 2, we have 3. No problem. Is there any problem with this? No problem, right? Okay. So I can do that, because try to understand that the span here, this span is identical to this span, and this span is identical to this span, right? So even though the graph paper wasn't linear, but if I consider this to be one span, this to be one span, and this to be one span, these widths are identical in nature, right? So if you forget all these lines, intermediate lines, okay, if I blindly consider this entire span, this width, if I consider this width to be 1, then this width is also 1, right? This width is also 1. These widths are identical, right? Try to see that at least. Forget all the lines here, all the intermediate lines. So if this width is 1, this width is also 1, this width is also 1. So I can, if I consider this to be 0, I can consider this to be 1, this to be 2, this to be 3. Of course, I can do that, right? Right? I'm only considering the thicker lines here. So this is 1, this is 1, this is 1. I'm just ignoring everything intermediate. I can happily consider that as if we have just 3 vertical lines, or rather 4 vertical lines in our graph paper. Like this is 1 vertical line, this is 1 vertical line, this is 1, this is 1, this is 1. I just have 4 vertical lines, 0, 1, 2, 3, equally spaced. Please feel free to let me know if you have any query with this. These are equally spaced, right? So if I just ignore everything in between, which I can, okay, this is going to be 0, 1, 2, 3. Quite understandable. All right. Again, pay close attention, and if you have any query, feel free to ask. Because anytime, or really rather every time you are going to see a frequency response plot, the plot there is a 100%, almost 100% likelihood that the plot will be done on this kind of a graph paper. Maybe on a computer, but on this kind of a graph paper. You would never have a plot that is on some other sort of a graph paper. And you will see how to do that using Python, for example. All right. So this is understood. If this I consider this to be 0, this is going to be 1, this is going to be 2, this is going to be 3. Let me erase everything here. Okay. I made a mess here. Let me erase. But I think I got the point through. Feel free to ask any question that you might have. So all I did was to ignore all the intermediate lines. So these lines are equally spaced. So this is the line we have been talking about. This is the line. this is, and this is. All right. No confusion whatsoever so far, right? I believe so. All right. My question is, now if this is 0 and this is 1, my question is, what would this one be? Let me use black. Oh, no, let me use red. My question is, what would this one be? What would this one be? If this is 0, this is 1, what is this one? Okay, this is between 0 and 1, some sort of fraction, right? Some sort of a fraction. All right. But how much? What is that fraction? What is that fraction? How much is that? Now, if you take a ruler and calculate the scale, so if this is 0 and this is 1, if this entire length is 1, so what we are saying essentially, by saying this to be 0 and this to be 1, what we are saying essentially is that this length is 1 unit. This length is 1 unit, right? This entire length is 1 unit, right? No, this is not 0.1. Does that look like 1/10 of this entire thing? If this is 1 unit, does this look like 0.1? I mean, does this look like 1/10 of the entire thing? You get my question? Does this distance look like 1/10 of this entire thing? If you divide this into 10 equal parts, would this look like one of those? Does this length look like 1/10 of this entire thing? Feel free to tell me, because it is not. Not even 1/9. Try to measure. I mean, maybe squint your eyes and try to measure, try to have a feeling. Not even 1/9. No, we have 10 lines, but forget about the lines. My point is, forget about these vertical lines. Forget about that for the moment. Forget about all those lines. I'm just telling you, how much is this distance? How much is this distance? Someone has a very close answer. This is about 35%. Maybe around 30% of this entire length. My question is this. If this length is 1 unit, how much is this length? How much is this length? If this entire length is 1 unit, how much is this length? I did not tell you, I did not ask you how much is this division. Someone is saying 0.01. No. How can it be 0.01? That would be very small, right? So if this length is 1 unit, say for example, if this length is 1 meter, how much meter is this? This will be around 1/3, right? Very close to 1/3. Look very carefully. This is kind of, sort of 1/3 or something close to that. Something close to that, maybe. Right? Right? Again, feel free to ask again if you have any query. At this point, I'm giving you an intuitive idea on reading this graph paper. Okay, understanding this graph paper. My question was, if this length is 1, how much is this length? This can't be 0.1 because that would be 10 equal divisions of this, and if you divide this entire span into 10 equal divisions, one division won't be that big. Not possible, right? Okay, so question is, how much or how big is this gap? How big is this gap? Okay, the gap we have been talking about is this. How big is this gap? Yeah, it's very close to 1/3, right? Very close to 1/3. But let's exactly know how much this is. So if you exactly calculate this, you would see that this gap has a length exactly of log base 10 of 2. Now question is, how much is that? And I will soon answer why these things are distributed like that. I will soon answer your question. But my point is, right now I'm asking you, what is the value of log 2 base 10? How much is that value? Can anybody tell me what is the value of log 2 base 10? Do you have a calculator? Yes, I do have a calculator. So let me show you. All right, let me bring the calculator here. Okay, and we have. So let me go to the screen. All right. I did not get that because that is how I'm telling you. I'm telling you. Okay. Okay. So this is 0.301. 0.301. Okay. And if you take, the thing is, this is how this thing is designed. If you take a ruler and measure up this much distance and consider that to be 1 unit, then using the same ruler, if you measure this distance would measure to be 0.301 unit, right? Yes, this distance would measure to be 0.301 unit. So if this distance is 1 unit, this distance, this length would measure out to be 0.301 unit. Okay, you would see that. Get the point? All right. All right. So this is how this thing is designed. For example, now, and again, forget about all these. Now, for example, at this point, we have a line that is 0.301 units apart from this line. From this vertical line, this is 0.301 units apart. All right. So this length is 0.301. So this is 0.301. So this length would be, so this is at length 0, this is at length 0.301. No issue with that? Got it? No problem, right? All right. All right. Question is, what is this distance then? What if you take the same ruler, okay, rather a scale, for example. If this length is 1 unit, how much would this length be? How much would this length be? And as it turns out, this scale is designed in such a particular way that this length is nothing but this, log 3 to the base 10. My point is, my question is, how much is this length then? Someone tell me, how much is this length? That's that logarithm, right? Let me take the calculator. Hold on. All right. And if I calculate, if I calculate log and say 3, that gives me 0.477. All right, 0.477. No issues with that. All right, so 0.477, happy. So this length is 0.477. We calculated that. So if you measure this, take this scale, measure this, it would be 0.477. Got it? Question is now, how much is this length? How much is this length? Yeah, this is close to the half, right? This is very close to 50%. This is actually very close to 50%. Okay. Yeah, one of you have already got where I'm going with this. I'm going to explain everything. How much is this length? As it turns out that this length is equal to log 4. But what is log 4? Log 4 is 0.602. Log 4 is 0.602. So if you of course, let's take the help of a calculator and say log 4. I'm saying log 4. Yeah, this is around 0.602. So this is going to be 0.602. This length is 0.602, right? Understandable? All right. Now what about this length? What about this vertical line? What about this length? Yes. What about this length? I mean, I'm asking you this. What about this length? Starting from here, going up to this point. What about this length? As it would turn out that this is equal to log 5. This is equal to log 5. Sorry. Log 5, right? So take this, log 5. That would be around 0.7. Alright. So this is around 0.7. Alright. Yeah, 0.69 around 0.7, so 0.7. Alright. No issues with that. What about this length at this point? What about this length? From this to this. What about this length? And again, if you calculate this, you would see that this length would be, rather if you measure this, that length would be log of, like that. So 0.78 to be very exact. 0. So this is going to be 0.78. Okay. And so on. Right? Okay. So again, if you measure this length, this distance, from this point to this point, it would turn out to be log 7. Log 7. How much is log 7? Let me just again calculate this. Yeah, around 0.84. All right. That's going to be 0.84. All right. All right. Let me zoom in. It's going to be 0.84, right? All right. Again, if I measure this distance from this point up to this point, how much would this length be? How much would this length be? As it would turn out, this is equal to log 8. Okay. And log 8 would be 3 times as much, 3 times of this. Of course, log 8 is 3 log 2 because of that. So this is going to be 0.903. This is going to be 0.903. Yes. Yes. And if I measure this length, this would be log 9. Log 9 is log 3 square, and that will be 2 log 3. So double of this. Okay. So let's calculate that for a moment. So 0.95. 0.95. And then what about this distance? This distance is already 1. We know that, right? So this is 1.0. Right? Right? Let me zoom in on this graph paper a little bit more so that you have a better view of everything. Let me try. All right. So now, at this point, I'm saying that if this length is 0, then what about this length? What about this? So this length is 1, right? Got it? Got it? But what about this length? This was just, let me take this. Okay, what about this length? This length was log 2. Can I say that? This length is log 2. Say that? This length is log 2. Right? Got it? What about this length? This was log 3. And look very closely, there is a 3 right here. How about this length? This is log 4. How about this length? This is log 5. How about this length? Log 6. How about this? Log 7. This is how much is it? Log 8. And this is log 9. Hold on. Huh? I might have to zoom this even bigger. I'm not entirely sure what I'm going to do with this. Okay, take this entire thing. Now I have a very, very large plot here. The point is, this is log 2. This is log 3. This is log 4. This is log 5. And this is log 6, this is log 7, this is log 8, this is log 9. Okay, I don't even have space to write log even after zooming this much. And this is 1, right? And this is 0. But what is 0? But what is 0? 0 is just log 1. All of you know that log 1 is 0. So this is log 1. And what is 1? This is log 10, right? The base of this logarithm is 10. So all these logarithms have a base 10, right? Of course. Otherwise, if the base was e, I would write ln. ln is natural logarithm where the base is e. And if I say log, so it has a base of e, and this has a base of 10, right? So these are the base of 10, right? All right, understandable? This is quite understandable, right? So now here we have the common logarithm. So this is known as natural logarithm. This is common logarithm. Base 10 means common logarithm. Why base 10? We have 10 fingers. Have you ever wondered why our calculation, why our number system has 10 digits? Why our number system is base 10 number system? Simply because, what happened? Hold on a moment. Someone seems to be foolishly burning all the tree leaves. Wow. Hold on. Anyway, so have you ever wondered why our number system has 10 digits, or it's a base 10 number system? Simply because we have 10 fingers. Our ancestors used to keep counts using our fingers like that. Since we have 10 fingers, we have a base 10 system. If we were some aliens where we had 6 fingers or something like that, our number system probably would be with 6 numbers, 6 digits. Yeah, someone just outside my home here, someone is burning all the tree leaves that fell during the cyclone. Yeah. Yeah. The way we learn counting when we were children is exactly the way our ancestors started counting. Okay. And when we are children, we start our counting from 1, 2, 3, 4, 5, 6, and so on. We are never taught 0, right? Because understanding 0 is not quite, what should I say, not easy for a child. No, not easy for a child, right? I can say here is one thing, so say this is 1, for example, right? But giving a child the idea of a 0 is very difficult. Right? I'm saying usual situation, not Rithi Roshan situation. All right. So with that said, so you understand what I have here. So I am starting my counting from log 1 up to log 10. Okay. Now let's go to the next one. Let's go to the next one. In the next one, this is again, how much unit is this? How much unit is this? Again, this is 1 unit. Right? We started from 0. Right? And this was 0.301. My question is now, how much is this length? How much is this entire length? Starting from here and going up to this. How much is this length? I am trying to measure this length. How much is this? Can somebody tell me? So this is length 0. Okay, which can be represented as log 1. Question is, how much is this length? Can someone tell me how much this length is? Of course, you don't have to calculate anything. Someone is saying 1.041. Why? Why exactly do you think that? This length is 1, of course. Yeah, this length is 1.301. Because this much is 1, right? This much is 1 unit. And this much is 0.301. Right? This much is 1 unit. This much is 0.301. Alright? This much is, yeah. I mean, someone said 1 plus log 2, you are correct. And someone said 1.301, you are also correct. You will see why. Okay. So this much is 0.301, right? So how much is this length, this entire length? 1.301. right? So of course my next question would be, how much is this length? Of course that would be 1.477, because this length is 1 and this length is 0.477. So we know that this entire length would be, from starting from this entire length would be 1.477. all right, but let's go back and try to now figure out what is this 1.301 thing. This 1.301 is 1 plus 0.301. okay, but what is 1? 1 is log 10, again base is 10 here. And what is 0.301? 0.301 is log 2. all right, feel free to let me know if you have any query, or if there is something you don't understand with this. all right, so this length is this length is, look very carefully, 1.301, right? Yes, you people got that already, right? So what is 1.301? So this is 1 plus 0.301. What is 1? That's log 10. What is 0.301? That's log 2. And what is log 10 plus log 2? That's log 10 into 2, right? So that's log 20. Okay, so I can now happily zoom in here and say that, okay, now I know that this length is log 20. okay, get that, right? Feel free to ask if you haven't understood this, because this entire length is 1.301, but what is 1.301? That's log 20. That's log 20, right? You get the idea, right? All right, let's zoom out once again. What about this one? 1.477. What about that one? 1.477. So that would be 1 plus 0.477. That would be log 10 plus log 3, because that was log 3, 0.477, and that would eventually become log 10 into 3. That would be log 30. Easy to understand? Easy to understand, right? So again, let me zoom back in. So this is 1.477. How much is this length then? How much is this length? This length is log 30. Of course, understandably, very quickly you can say this is going to be log 40. This is going to be log 50, log 60, log 70, log 80, log 90, and say this is just log 80, for example. This point is log 80, and this is how much? My question is, let's go back. How much is this entire length? This length is 2 units, right? This length is 2 units. And what is that thing whose logarithm is 2? So for example, this entire length is 2 units, right? This entire length is 2 units, and 2 can be written as, so this is 2. 2 is 1 plus 1. This is log 10 plus log 10. That's going to be log 10 into 10. How much is that? Log 100. So I can zoom this in, and I can now say this is log 100. This is log 100. Yes, that's 2 log 10 or log 100. Got it? Now so this started with log 1, log 2, log 3, log 4, log 5, log 6, log 7, log 8, log 9, log 10, and then log 20, log 30, log 40, log 50, log 60, log 70, log 80, log 90, log 100. Now I'll give you 2 minutes, and I will let you I will let you think about what happens in the next cycle. I will let you think about what happens in the next cycle. Okay, I'll give you 2 minutes to think about that and come up with the answer in the live chat. I'll be back in 2 minutes. All right. Someone is saying log 2000. Someone is saying log 1000. All right. So yes, those who have got this, I think it's all right. So let's zoom back in slightly. All right. So take this one. Of course, this is 3. Of course, that's going to be that number whose logarithm is 3. That's going to be log 1000, right? That's going to be log 1000. So I can just zoom in a bit and say, of course, this is going to be 2.301. This length is going to be 2.301, which is going to be log 200, right? This is going to be log 200. Okay, this is log 300 and so on. So log 200, log 300 and so on up to, so this is 3 and this is going to be log 1000, right? So we started our computation, started our calculation rather from log 1 and we ended up at log 1000, right? So now this is what happens whenever we are actually plotting using this kind of graph paper, plotting using this kind of graph paper. What happens is, if this is my frequency, for example, if in this axis I have frequency, then we are dealing with frequencies which is, say for example, corresponding to 1 here, and then 10 here, then 100 here, then 1000 here. So instead of writing log 1, log 2, log 3, log 4, log 5, and say log 20, 30, and log 200, log 200, 300, and so on, instead of saying all these, what we instead say that this is a logarithmic scale. In the horizontal axis, we have frequency, and the frequency is in logarithmic scale, and these are the frequency values corresponding to this. Imagine the frequency is in terms of the logarithm, right? So if this 1, 2, 3, these things are frequencies, then we would say, let me erase everything here, then we would say that we are now talking about a frequency of 1 radian per second here, or maybe 1 hertz here, based on our units. This is 2, this is 3, this is 4, this is 5, 6, 7, 8, 9, and 10. And then we have frequencies like 20, 30. Again, this is corresponding to log 30. Okay, 40, 50, 60, and so on up to 100. Then we have 200, 300, 400, 500, and so on up to 1000. Right? So this is going to be my range of frequencies, right? Frequency omega. So in my frequency response plot, what happens is that I use a graph paper that has a logarithmic frequency axis. So frequency has already got a logarithm on top of it, okay, to give you a logarithmic frequency axis. Okay, again, the entire idea is built upon how we perceive things, is built upon our logarithmic perception. Okay, we perceive things logarithmically. So from 1 to 10, for example, if we increase from 1 to 10, that's a 10-fold change. Then from 10 to 100, that's also a 10-fold change. Then from 100 to 1000, that's also another 10-fold change. And again, since this is a 10-fold change, this change would perceived identically to this change. So this change is a 10-fold change. This is again a 10-fold change. 10 times, right? This is again a 10-fold change. So if something increases from 1 to a 10, the perception we would have in our mind is identical to something changing from 10 to 100, because that's again a 10-fold change. We understand or perceive things multiplicatively, right? Then if something changes from 100 to 1000, then again that would be a 10-fold change, and again we would perceive that identically. So all these changes are perceived identically. So this one change, one 10-fold change, is known as one cycle. This is known as one cycle. This is another cycle, and this is another cycle. Okay, So in very particular example, this is a 3-cycle graph paper. Okay, right? So how many cycles in the logarithmic axis do you have? You have 3 cycles in the logarithmic axis, right? In the logarithmic axis, so this is the logarithmic axis, the horizontal axis is the logarithmic axis here, or rather the frequency axis we are going to use. This is a 3-cycle graph paper. And what kind of 3-cycle graph paper? Look very carefully. This graph paper has a logarithmic axis in only one of the axes, right? There are 2 axes in a planar graph paper. For example, you have the horizontal axis and the vertical axis. Look carefully, the vertical axis is linear, okay, but the horizontal axis is logarithmic in nature. And just a moment, YouTube is still giving me trouble with the live chat. Okay, so this graph paper in particular is known as a semi-log graph paper. Yes, it does exceed 3 cycles. You can go to a shop that sells this kind of graph papers, and you can buy a graph paper of 3 cycles like this one, or you can buy a graph paper of 5 cycles. Okay, I mean, getting a graph paper for more than that is not really a good idea, right? For any practical purpose. If you're hand drawing things, if you're doing it using a computer, you can of course do whatever, however many cycles you want. But as far as the things you can purchase, you can usually purchase a 3-cycle graph paper or a 5-cycle graph paper. Okay, got it? And this is in particular known as look carefully. See, one of the axis is logarithmic. So this axis is logarithmic. So this is the log axis, and this axis, this vertical axis, is the linear axis, right? This axis is the linear axis, this is the logarithmic axis. So since not both the axes are logarithmic, this kind of graph paper is known as a semi-log graph paper. So stands for semi-logarithmic graph paper. So one of the axes is logarithmic, the other one is linear. That is why semi-log, right? Semi means half in this scenario. Semi, hemi, this kind of prefixes, they mean half, for example. Okay. So semi-logarithmic means half logarithmic. Only one of the axes is logarithmic, the other one is linear. The vertical axis is linear, the horizontal axis is logarithmic, right? So this is called a semi-log graph paper, and specifically, this is a semi-log 3 cycles graph paper. This is a semi-log 3 cycles graph paper. Okay, you get the point? So why 3 cycles? Because we have 3 cycles of frequencies. All right. No problem with this, right? Let me give you a slightly more rather involved example momentarily. Hold on. We shall talk about that in the next class. Someone is asking what we can do about the vertical axis. We shall talk about that in the next class, of course. We took a lot of time to discuss the semi-log part here. All right. So again, we shall talk about the vertical axis in the next class. Okay. Now again, let's go back to a primitive idea, the initial idea we had. So initially, as per our initial idea went, we considered this to be length 0, length 1, length 2, and length 3, right? And accordingly, this gave me log 1, this was log 10, this was log 100, this was log 1000, right? That was like that. So this was log 1000, right? It was like that. All right. But as linear, so again, if I take these thicker lines here, this looks like a linear graph paper, right? So this is length 1, this is another length 1, this is another length 1. But I could also consider this to be length 1, this to be 1. Just in any graph paper, of course, you can do something like this. You have these axes, right? You can consider this to be 1. You can start from 1. You can say 2. You have 2 here, 3 here, 3, 4 here. Okay. No one is saying that you have to consider the starting point to be 0, right? You can have 1. You can have 2. You can have -1, whatever, right? You can have any other value as a starting point, right? You get the idea, right? Instead of saying 1, instead of saying 0, we can start from 1. We can start from 1. Right? And if we start from 1, then this is going to be 2, this is going to be 3, this is going to be 4 in terms of the lengths. In terms of the lengths. And if this is 1 in terms of the length, then this is actually corresponding to a log 10. And if this is 2 in terms of the length, again, we're just assuming that initial point of the axis, we are assuming that to be okay, someone is saying, yeah, we are discussing that. Someone is asking what frequencies, can we change the frequencies as per our convenience? Yes, we are actually doing that right now. So this is log 10. Then of course this is going to be log 100. This is going to be log 1000. And this is going to be log 10,000. You get the point, right? And based on that, of course, if this is 1, this is 2, this is 3, this is 4, as far as the length goes, as for the frequencies we are writing out, so this is going to be 10 hertz or 10 radian per second, right? This is going to be 100 hertz or 100 radian per second. This is going to be 1000 hertz or 1000 radian per second. This is going to be 10,000 hertz or 10,000 radian per second. Of course. So now we can, of course, take any 3 cycles. This is a 3-cycle graph paper. Look very carefully. This is again 3 cycles. So any one 10-fold change is known as a cycle or a decade. Okay. So this is again 1 decade or a 1 cycle. So 1 cycle or 1 decade, whatever you call it. We often sometimes call it decade, or sometimes call it cycle. Okay. So we have 1 decade here. So from 10 to 100, that's a 10-fold change. It's a 1 decade. That's another 1 decade. So from 100 we have 1000. That's another decade. This is another decade. In logarithmic scale, decade means a 10-fold change. Okay, decade is not a 10 years, right? So 10-fold change. So frequency is changing by 10-fold or increasing by 10-fold. So this is going to be 1 decade, 1 decade, 1 decade. How many decades or cycles do I have? I have 3 decades or 3 cycles. All right. So starting from 10 hertz or 10 radian per second, I'm going up to 100 hertz, 1000 hertz, 10,000 hertz, and so on, or 10,000 radian per second as far as goes. And I'm again refreshing the YouTube live stream. I have to figure out what is happening here. I think you are not having any trouble from your point of view, but I am having a lot of trouble with the live chat. It is not refreshing automatically. All right, so yeah, that's understood, right? Let's now again go back. Let's bring this graph paper once more. Let's bring this graph paper once more. All right, let's bring this graph paper, and I think it's fine. All right. Just like the previous one, I can now consider this to be -1, length -1. Just like, of course, we can have a graph paper axis, and we can consider this to be -1, then this to be -2, then this to be -3. That's quite usual, right? We can do that. No one is stopping us from doing that, right? So this is -1. I can say that. Then this is going to be 0. This is going to be 1, and this is going to be 2. Right? So of course, whose logarithm is -1? That's going to be log of 0.1. So this is going to be log of 0.1, right? So again, this is log 1, this is log 10, this is log 100. Got it? So log 0.1 is, of course, you know that log 0.1 is how log 0.1, that is log 10 to the power minus 1. So of course that is going to be minus 1 log 10, and log 10 is 1, so that's minus 1. So you understand that. Anyway, so again in terms of frequency, so if I consider that frequency to be in logarithmic scale, so this is going to be 0.1, this is going to be 1, this is going to be 10, this is going to be 100. But look very carefully again, we have 1 decade here, right? We have 1 decade here, we have 1 decade here, and we have 1 decade here, right? So we have 3 decades. Once again, we have 3 decades, right? 3 10-fold changes. But look carefully here, this frequency is going to be 0.2, this is going to be 0.3, this is going to be 2, and so on, right? This is going to be 3, this is going to be 20, this is going to be 30, this is going to be 90, for example, this is going to be 9, this is going to be 0.9, and so on. And the previous one, for example, this was 20, this was 30, this is 200, this is, for example, 400, and so on. This is, for example, 2000, this is, for example, 9000, this is, for example, 900, and so on. So feel free to ask me any question that you might have about the understanding of this logarithmic graph papers. Right. And we shall quickly jump into Google Colab for a bit of programming, and just I shall modify the program that we did in the last class, just modify the program a little bit and change that graph paper into a semi-logarithmic graph paper, like one we have just studied today. Okay, we shall change the graph paper into a semi-logarithmic graph paper, and we shall plot everything, and in the next class we shall wrap everything up by describing. Yeah, you can only change it by 1 decade. Unfortunately, you cannot consider it to be, for example, minus 1 point something like that. If you do that, you would automatically cause issue with that, right? Automatically, because it has to be 0 or 1 in order for this to properly propagate, right? So for example, if you consider this to be 0.3 and accordingly take the logarithm for that, then of course you would have the multiplicative property, right? So for example, instead of considering this to be 10, try to understand, instead of considering this to be 10, for example, if you consider this to be 15, right? So this is going to be 30. This is going to be 2 times of that. This is going to be 45. That's going to be 3 times of that. This is indeed going to be 150. Okay. This is indeed going to be 1500. This is indeed going to be 15,000. That property is going to be held true. Okay. If this is 15 or corresponding to the log 15, whatever value you have, then this is going to be corresponding to log 150, because that's going to be log 15 plus 1, right? Similarly, this is going to be log 150 plus 1. That's going to be log 1500. Similarly, this is going to be log 15,000, and so on, right? But that's not the standard norm. Okay, that's not the standard norm, but you can do that. You won't be violating any mathematics whatsoever. Okay, the mathematics of the graph paper will not be violated, right? So if you consider this to be 15, okay, that's how the things will change. If you consider this to be 1.5, this is going to be 15, this is going to be 150, this is going to be 1500, right? If you consider this to be 0.3, for example, this is going to be 3, this is going to be 30, this is going to be 300. You get the point, you get the idea, right? So whatever you consider here, things will change. in decades, right? That will be a tenfold change, that will be a tenfold change. And here, of course, if this is 0.3, then this is going to be 0.6, then this is going to be 0.9, then this is going to be 1.2, and so on, and so on. Right? Similarly, this is going to, if this is 15, if this is 3, this is going to be 6, this is going to be 9, and so on. This is going to be 12, and so on. If this is 30, this is going to be 60, 90, 120, and so on. Yes, the multiplicative nature will remain identical even if we change the initial, the first value here. Accordingly, everything will change. Accordingly, everything will change. Feel free to ask any question that you might have. We are going to quickly jump into Google Colab and modify 2 or 3 lines in our program that we did earlier, and accordingly we shall generate a logarithmic scale. Okay, and of course, whenever you are doing frequency response plot of anything, you are supposed to use a logarithmic scale. All right, so that small changes in frequency are emphasized, high changes in frequency are also emphasized. So everything would get sort of an equal emphasis in the plot, right? Again, everything is based on our logarithmic perception. So small changes in small frequencies are perceived identically to large changes in large frequencies. That is the whole point here of describing frequency responses. So again, I'm refreshing the live stream because I'm refreshing the live chat because it is not refreshing automatically. Something is preventing it from doing that. All right. So this is clear, I think, right? So let's jump into Google Colab and let's see what we can do about that. Do I have Google Colab opened? No, I don't think so. Let me open Google Colab and I'll be back. And I have already shared this file with you. I'm just editing the shared file. Okay. I'm just editing the shared file. Anytime you open the shared file, you can go back and open the shared file, and automatically these changes will reflect to you. Okay, this is the file I shared in the last class, in our last class. So let me just modify this a little bit. Okay. Again, the initial run takes a while. All right. So I'm not describing the frequency response and everything, right? You already probably have the ideas on this, right? You probably know what I'm talking about. Right? And if you don't, please go back to the previous classes, right? Now here we actually plotted everything in a linear scale, right? But I don't want to do that. Instead, I want to plot everything in a logarithmic scale, right? Now, so instead of this being lim space, now this is going to be log space. Okay, log space is logarithmic space. Okay, and say I'm trying to check from -1. So -1 in terms of logarithm, right? The frequency is going to be log of mine. So the corresponding logarithm of that, right? So it's going to be 0.1. So -1 means 0.1, right? So 10 to the power -1 actually, right? And this is going to be, say for example, 1. So I'm checking 2 cycles here. Okay, so 10 to the power -1, which is 0.1, then 1, and then 100, then a 10, right? Something like that. So of course log 10 is 1, log of 0.1 is -1, and of course in between you have 0, and that's log 1, right? And we are taking 100 points. Okay, now instead of this plot being just a plot, okay, just a plot, instead of using the plot command, we shall use this command, semilog x. it tells Python that I want a semi-logarithmic graph. It tells Python that I want a semi-logarithmic graph, and there the logarithmic axis needs to be along the x-axis or the horizontal axis. That is the semilog x command. Semilog x, this function gives you a logarithmic graph, or rather semi-logarithmic graph, where the vertical axis is linear but the x-axis or the horizontal axis is logarithmic. So semilog x. Okay, the same thing will remain. And grid, here I'm just writing something within the grid. I'm just modifying it a bit. I'm writing which, I'm saying both, which equal to both. Now can you see this, that we have now a logarithmic graph, okay, or rather a semi-logarithmic graph. Look very carefully. The frequency has now been from 10 to the power minus 1 to 10 to the power 1. So what is 10 to the power minus 1? That's 0.1. This is 10 to the power 0, so that's 1. And this is 10 to the power 1, so that's 10. All right. So we now have a semi-logarithmic graph paper to plot our frequency responses. Okay. All right. So this is how you actually plot the frequencies. Again, and in the next class we shall learn how to change this from absolute values to decibel values. Again, amplitudes are plotted in using in a decibel scale, and decibel scale itself is a logarithmic scale, and we shall discuss that in the next class again. Okay, so these are the changes that we made here. So similarly here for this particular plot, again we shall do log space, and if you have any query, feel free to ask. Again, we are plotting from 0.1 radian per second to 1 radian per second. So here I'm going to make this minus 1 to 1. So minus 1 to 0, for example. Yeah, minus 1 to 1. All right, minus 1 to 1. So this is going to be from 0.1 to 10 radian per second, right? And I'm going to take 100 points there. Oh, sorry, why am I changing? That was the value of R. I'm not supposed to change. Yeah. So 0 frequency. So again, so let's consider that to be 0.1 to a 10. Okay, 100 points and X level. And here, instead of doing plot, I have to do semilog x and axis which equal to both. And this which equal to both actually gives you the proper axis labeling, right? All the lines are properly drawn. That's the thing. There's no other differences. Okay, let me just increase the number of points we have, intermediate points. Right. So now this gives you a kind of a better understanding of what is happening inside this. Okay, this sort of gives you a better understanding of what is happening. The idea is that this tells you rather more properly that it's a low pass filter. Okay, you can see the lower frequencies are passed through by the filter unchanged, and that's more prominently visible here. Okay, this phenomena that it is allowing lower frequencies to pass unaltered and it's blocking higher frequencies, this phenomena is more prominent or more promptly displayed here. Okay, you are seeing lower change, small changes. We shall talk about decibel, and someone of you has actually given the formula for decibel. Yes, we are actually going to use that later on in the next class. But the idea is, if we just plot everything in logarithmic scale, we see that the low pass filter nature of this thing is more prominent. We are seeing that low frequencies are given, what should I say? We are seeing that low frequencies here are getting more prominent picture here, right? We are getting to see low frequencies, or rather, instead of saying lin space, say log space. Rather, from this, instead of saying this, all right, so do that. We have plenty of, yeah. So now look carefully. So this is actually showing you that this is a low pass filter and everything is quite prominent. What facts are prominent? That low frequencies are being passed unaltered. So this kind of facts are quite prominent here. And then here the axis is the logarithmic axis that we actually discussed in our earlier class. So this, again, make this log space, and let's make this from 10 to the minus 1 to 10. Let's take 1,000 points, make this semi-log x, and here let's do that. Okay, you have to run this first. Okay, this function wasn't defined otherwise. Yeah. Right? So now probably this is kind of showing you a symmetry in the system, right? Previously this plot wasn't looking symmetric. Now this is kind of looking symmetric. Okay, this was the amplitude response of our RLC series circuit, right? Okay, and again it is showing you it's blocking lower frequencies and it is blocking higher frequencies. This was the band pass filter. Okay, and again we shall discuss these intricate details in the next class while we discuss the decibel scale and everything. Right? Now we have a symmetric plot, for example. Right? Alright, good. So you have a logarithmic axis again, logarithmic frequency axis, right? So frequency starts from 10 to the minus 1, goes to 10 to the power 0 and 10 to the power 1. And again I'm refreshing the live chat once more. Same thing here. If I take log space here from 10 to the power minus 1, go up to 10 to the power 1 and do a semi-log x, and do a which equal to both. Hold on. Let me plot this. You kind of now have a better plot representing everything. How this is kind of actually a low pass band pass filter, and how it discriminates higher and lower frequencies about the corner frequency that we have here. Okay, that discrimination is quite properly visible. In the previous plot, it did not look like that. Okay. So yes, logarithmic scale gives you better understanding of the underlying changes. So again, make this log space, and make this from 10 to the power minus 1 to 10 to the power 1, and make this semi-log x, and say which equal to both. Right? And again, you kind of have a better understanding that it is actually blocking lower frequencies, and the corner frequency is shifting because we are changing the value of L. Okay, and probably we shall discuss all these things in the next class. With that said, so these are the changes that you are going to I have just saved all the changes. I shared this file in the last class, and I shall do that again after today's class. So you are supposed to go through this and again try to manipulate the values, and this is how we actually plot frequency responses. Whenever we are plotting frequency responses, frequency will always be in a logarithmic scale, okay, in a semi-log graph paper. That is what it is supposed to be, right? Because we want to emphasize small changes in small frequencies and large changes in large frequencies, because that is how we perceive changes, right? So that will be the end of today's class, and we shall arrange another meeting for regarding the exam shortly. So don't worry about that. Actually, I shall write you an email regarding the exam. So, and let me assure you, there is nothing much to be worried about. All right. So with that said, if you have any more any queries, I shall discuss this. Otherwise, we are going to end today's discussion at this point. Again, feel free to ask any question that you might have. So in today's discussion, we have understood why logarithmic understanding logarithmic perception is important, because everything is perceived by us in logarithmic scale, using logarithmic scales. We have logarithmic perception. Okay, we understand things multiplicatively, not additively. Our perception, all our senses are not linear but logarithmic in nature, right? And we use that in all our frequency response analysis. Okay, we measure frequencies in a logarithmic scale, and we have learned how to use Python to calculate frequency response in a logarithmic scale. We have learned how to read a semilog graph paper. Okay, and in the next class we shall learn how decibels and all those ideas come into effect, and we would have a concrete idea of frequency response of systems. Okay, and probably the next class is going to take place on this Friday. All right. So with that said, if you don't have any more queries, we are going to end our discussion today. Thank you very much for being here. I shall see you on Friday. If something doesn't go wrong, there is every possibility of everything going wrong. Anyway, so be safe, stay safe, and I shall see you on Friday. I shall be here one more minute. If you were writing any question, I might be able to get that. Otherwise, if you have any question later on, feel free to send that to me via email. I shall definitely answer your questions. All right. And as your homework, I am asking you to play with this this thing. Okay, this Python programs, and try writing different frequency response functions and see how these things really change. Okay, so try doing those. All right, thank you, and see you back on Friday.